Welcome back. So we are embarking on lecture 10, and we are speaking today about a super interesting topic. We're speaking about maximum likelihood estimation in an applied setting. And we will further talk, here we go. Okay. This. Okay, so we're talking today about the maximum maximum likelihood estimation. We're revisiting maximum likelihood. We discuss again the principle, and we will also do maximum likelihood estimation for logistic regression. So today we're going to dig a little deeper into MLE. We will further talk about the classification of predicted probability, classification in terms of a true negative and a true positive rate, as you know from your API classes. And I believe from previous biostatistic classes, you know about specificity and sensitivity, the true positive and true negative rate, and the corresponding false negative and false positive rate, equally important, and the ROC curve. So the receiver operating characteristics curve is a means to essentially plot sensitivity as a function of 1 minus specificity. So this is sensitivity, the true positive rate, as a function of the false negative rate, which essentially allows for you to see the diagnostic performance of a test over your entire range of entries in your data set. And this is, as you can think and as you can imagine at this point, I'm not sure you had an introductory lesson on the ROC curve already, but we will be discussing that already today in principle, in broad strokes. We will talk about how to determine thresholds based on this curve that you're generating and why this is a useful test. In lab 10 today, we will, and this will be a separate part, we will talk about an R code, how to generate an ROC curve. So there are various packages out there. There are various ways and approaches how to do that. We will be discussing one today. Maybe I'll show you the second one. Okay, so some issues and some notes on the research note 1. So one of the problems that were quite common, and this is observations that I'm sharing with Professor Sang. So many did not have a title on the research note, and research note 1 is not a proper title. It should have a title. There should be a description of the sample in the text. So table 1 alone is not sufficient. So it should really be table 1. What does it show? This table 1, meaning it's either we should have a description of what this table actually shows. We should have descriptive statistics of the outcomes and the study variable. So it should be shown what the descriptives look like. And descriptive statistics need to be shown in a certain way or form. So characteristic, it's a mean plus minus a standard deviation, or a median and the 25th, 75th percentile. That's a common way, or alternatively also min or max. I would usually do 25th, 75th percentile, but this is to be seen individually. Usually when you do prepare your descriptive statistics, a lot of times journals and editors do have their preferences. Reviewers may comment on it, how they want you to present it. So it's sometimes a little bit of a negotiation base, but it's always, what is important, that you always have a central tendency as well as variability parameter. Okay, linear regression models. We have talked about these on the left side, a predicted YI. On the right-hand side, we have intercepts, covariates, and the respective predicted slopes. And the maximum likelihood estimations essentially will allow for an estimate of these coefficients. So the logistic regression model, analogously, we have a log of the odds, which is actually the probability of an event occurring over the probability of the event not occurring. And this is fitted with a logit function to allow for a log odds estimation in a linear setting, because usually it would not be linear. So you are employing a logit function to kind of be able to estimate it in a linear way. So if you're using now data of yi, you essentially, you have I from 1 to n, and you have covariates from j to p, which we know is the number of covariates. So these betas can be from 1 up to a maximum of p. So the maximum number of p's will be contained within this beta j. So for this equation, we can use least squares to minimize our sum of residual differences between the estimate and the predicted estimate. So this difference is essentially squared, summed up, and you want to minimize those to essentially find the optimal coefficient setting for all your entries in your data. So for 2, it's a little bit more complex. And if we just in principle focus now on yi as a function of mu and the residual error I, where the residual error I as the residuals is normally distributed around the mean of 0 with a variance of 1 or a standard deviation of 1, where mu is the only unknown parameter and sigma, or the variance, equals 1. So essentially the model transforms them with when only one parameter is not known to yi equals a normal distribution of mu and 1. So if we have now 2 sample points, y1 and y2, and we guess an estimate of mu to be mu hat 1, then we can choose a value for the mu. That means we can estimate it based on what we have. So, and when we choose this value for mu, we have now a complete probability density of our data. Probability density being the functions of our normal distribution. You remember that the normal distribution essentially is mathematically defined as a function that looks essentially like this up here. So we basically were looking at this as a function, and I think I've shown that function to be mapped out in an Excel spreadsheet in one of the earlier classes. Please go back to the recordings and find this. And this becomes now here the so-called sample likelihood. So again, we're reducing the model now to yi equals mu plus a residual error I, and the residual error I is considered to be normally distributed around the mean of 0 with a variance of 1. And this model basically reduces even further to yi being a normally distributed distribution around a mean of mu with a variance of 1. So now this is obviously this. If you're reducing it to that way, you can use this for the estimation of coefficient values, and this is essentially where we're going with the maximum likelihood estimation. Okay, we're plotting this normal density function with a mean of mu and a variance sigma square. We are getting to a function of y mu and the variance sigma squared. And this equals our distribution function, our normal distribution function. And because we have a random sample and a guess estimate of mu, the sample likelihood becomes now our likelihood of this predicted mu in our sample is essentially a function of our y1, which we have two, right? Y1 and y2. We said we would estimate this with two sample points, y1 and y2. So now we have y1, essentially, we have a function of y1, mu hat 1, our estimate, our first estimate, and a variance of 1, multiplied by, and this is where it becomes a maximum likelihood estimation. We're building a product between our estimates. So we have now a certain outcome, a certain probability of our y1 found here, a second one here, and we're multiplying this because it's two independent randomly picked samples. So we have now a numerical example shown here by Professor Sang. So we assume now that our y1 is 0.5, our y2 is 0.4, and we're supposing, and we're essentially estimating our first guess to be mu hat 1 to be 4. So that's the initial guess. So now we get to a likelihood of 4. This likelihood of 4 is a probability of y1, 0.5, and y2, 0.4, with a mu of 4. So now this probability essentially is shockingly low, and it was a pretty bad guess, obviously, because if you take a mu of 4 and you're taking a variance of 1, you can only imagine how far off your 0.5 is going to be, right? This is not really where you want it to be. So how do we interpret this? So if our observed data is characterized by y1 and y2, then our estimated guess of mu hat 1 of 4 is actually pretty terrible. So essentially we need to do better. And this is what you do, because you need to look at this probability density function, and you see this is your assumption, right? This is your assumption that this is your mu. And this mu is essentially your coefficient in broad strokes. So you have now a yi and a y2, and you are trying to predict it with your estimated mu of 4. And essentially your yi is somewhere here. So this is obviously quite small likelihood, right? So it was a terrible guess. So how could we do better? We tried with different numbers. So we're trying it with 2. So here it's getting a little better. So it's getting a little better, and essentially the way you're getting to this is by taking the actual probability under the probability density function, which is here 0.4 and 0.5, and you're multiplying these two. So the likelihood increases now compared to 0, obviously, because the probability, the likelihood would be in worst case scenario, if it's really off, it's 0. So now how you essentially can update these estimates is by essentially using different mu's and determining different probabilities. And this you can easily do with a norm dist function in Excel, or you can do it with also with functions in R to map this out. But the sample likelihood here essentially is increasing here up to a maximum that you essentially want to reach. And this essentially converts them to a minimum when you logarithmically transform it. So it turns out for this example that the best guess would actually be a mu of 0.45, which is also not entirely unlogical, because essentially it's right between 0.4 and 0.5, right? So if you are building now, your mu hat MLE is now the sum of these probabilities divided by the n. So essentially it is to some extent an average probability between the available data. So The way you would do that, so you get a sample, you guess an initial estimate of the parameters, you construct the sample likelihood, which is the product of each sample unit's probability under the initial estimate. You iterate step 2 and 3 until a maximum of sample likelihood is reached. So which means you're repeating exactly these entries as often until you have reached a maximum estimate, which is here either a high likelihood or a small sample log likelihood. Okay, good. So for a linear regression analysis, we have a comparable kind of situation. We again have the yi equals beta 0 and beta 1 xi, and the residual error of I, which essentially is a normal distribution around a mean of 0 with a variance of sigma squared. Yi again transforms here in a beta 0, which is our intercept, and beta 1 xi around the variance of sigma squared. So the log likelihood is again the product of all probabilities for your estimated yi, and essentially again follows the same distribution. The maximization of 5 is essentially equivalent to a least squares procedure, where you essentially mean to minimize the differences, and the formula are equivalent. So a simple logistic regression with maximum likelihood estimation is essentially now the logit of pi. So this is the probability of an event occurring over not occurring. So essentially we are getting now beta 0 plus beta 1 xi, where the probability I is the probability of yi equals 1, which is the probability of our event occurring. So pi here is again under the normal approximation and under the assumption that with a large repetition of sampling from the same population, you will get a normal distribution around your prevalence or probability of an event occurring. You essentially can now equate pi to the odds of an event occurring. So this is the probability of an event occurring divided by the probability of the event not occurring. So 1 minus pi essentially now is 1 divided by 1 plus that estimate. For the sample likelihood, we have now log likelihood of an event occurring, the log of the product of the probabilities, and essentially gets you with a mathematical trick that the professor Sang is labeling here as a trick to essentially, and this is where this only can, yi can only take a value between 0 and 1. And by that, you essentially get to a maximum likelihood estimation of the logistic regression. So the log is minimized for computational stability, and analytic derivations such as the Newton-Raphson algorithm are often used. Global maxima are not guaranteed, and different initial estimates are recommended. So if we're fitting now a binary outcome for multiple logistic regression, we're getting, so for the log odds, we are essentially getting here the p hat I as the very same odds in the same fashion as we have seen it to be spelled out here, just with additional covariates. So this essentially will allow for us to now get us to cutoff points and to for us to determine whether an outcome is going to occur or not occur. So if we have a negative PI, this is essentially where the p hat I is smaller than 0.5 versus a positive p hat I, we essentially get a negative and a positive outcome of our predicted outcome. So that means if it's greater than 0, the log odds are basically greater than 1, the odds ratio is going to be greater than 1, and the log odds smaller than 0 are essentially less than 1. So this being said, so this probability is here smaller than 50%, whereas here the probability is greater than 50%, meaning this is how you allocate and classify between the rows. So you have outcome on the columns, and you have the actual diagnostic on the rows. So meaning if it's likely to occur, you essentially classify it in the first line. If it's likely to not occur, you classify it on the second row. So if this indeed is, wrong, sorry. If it's, obviously it's positive, sorry. So second line is if, and this is also, this is, okay. So this is where I got misled. So actually outcome is here, yes, and this is actually on the second column. So essentially these are your true positives, whereas these are your true negatives. So I'm used to kind of look at it in reverse fashion. So I have my true positives here where A is, so that kind of threw me off. Apologies for that mix up. So actually we have positive where the p hat I is greater than 0.5. So the probability is greater than 50%, or the odds ratio is greater than 1. So essentially you have here the D as being the true positive, whereas you have the B as being the false negative. Concomitant, analogously, you have your true negatives as the A, and you have your false, no, you have your false positives here as your C. In the same function, and this is how you will essentially judge the accuracy, the diagnostic accuracy of that logistic regression that you have built here using the prediction of your delta and your p hat I. So this multiple logistic regression essentially gives you positive outcomes, which is your D, which can be true or not. If it's not, it becomes a B, that's your false negative. If it is indeed negative and your model predicts it as negative, it becomes an A. And if it is indeed negative, but your model predicts it should be positive, it becomes a C. So we know that the specificity as the true negative rate is calculated as the true negatives divided by the true negatives and the false negatives. So this is A divided by A plus C. Whereas the sensitivity, the true positive rate, is calculated as the true positives divided by the true positives and the false positives. So these are, sorry. So A is the number of subjects classified to be negative when the true outcome is negative, true negatives. D is the number of subjects classified to be positive when the true outcome is positive, false, true positives. So this probability can then essentially, as we discussed earlier, this can be shown for all your estimates and for your entire range of potential thresholds. And this is essentially what we're looking at with in our lab. So if we are using the admit dataset, we can look for predictors of admission to a certain university. We can look this at the results of the GREs, the results of the GPAs in your early education or in of the students that are applying. and the rank like of the university. So essentially we have, in the same fashion, we're building a logistic regression model. We have a probability, we're predicting this probability based on that fit over an entire range of our data. And we can now look at sensitivity and specificity with a threshold that we can define here. So this would look as follows. Okay, so I prepared now. Oops. So this is not the lab yet, but I want to show this because I think it's quite interesting to look at this actual data. So we have the Haven library. We are loading the DAT data set, which is 400 observations. So these are 400 students. Now we're building a fit. So if we look now at summary fit, we can already kind of look at what this data will look like. And so now we see that the GRE counts, the GPA count, the rank of the university is also quite strong, in fact. So GPA and the rank of the university matters the most. So now we're calculating a probability for each individual. So if we are building probabilities and we're using the predict function here, we get predicted values for each entry. So that means that probability is here a vector of 400 probabilities, which are essentially consistent with the 400 entries in our data. So if we are mapping out this probability, we're seeing here the same distribution that we see here in the lab, in the lecture. And now we're building decision, yes, no, for our probability. So we are getting now decision, and decision equally is gonna be a 0 and 1, a vector consisting of 0 and 1 that essentially will allow for us to now calculate the sensitivity, the specificity of our sample. So essentially it does nothing else but summing all entries in MYT, MYT. MYT is here table decision. So MYT looks in depth, shape, and form. So we have here MYT, right? And this already gives us a start for our lab. So sensitivity and specificity. So again, we have here true positives, true negatives. So specificity is MYT 1, so that's true negatives, divided by true negatives plus our false positives. Yeah, no, yeah, false positives, yes, false positives. Then we have here our true positives plus our false negatives. Okay, true positives, false positives, false negatives. Okay, so now, yeah. Okay, so now essentially we are calculating now 2 divided by 1 2 plus 2 2. So that's specificity, that's sensitivity. I still keep on getting mixed up. So again, pay attention, and I think I mentioned this already. So this is more of a data science way how to depict this data, and you need to make sure that you understand rows and columns, otherwise you're gonna struggle just like I'm struggling. So in epidemiology, we always built like, here was outcome positive and here was decision positive. So now data science essentially has work with it, and Professor Sen here uses a more data science inclined approach to depict the contingency table. So it's important to keep in mind that you understand what data you're looking at and how. Good. So let's go back. So this is the receiver operating characteristics curve. So I have no idea where I did that. Okay. So this is the receiver operating characteristics curve. And I said this is your sensitivity as a function of your false negative rate. So when you look at this, so you have sensitivity here. Sensitivity is true positives divided by true positives minus false negatives. That means that you essentially are looking at sensitivity. These are the ones that essentially from your population of admitted students did really get admitted based on your logistic regression. Whereas the false positive rate are the true negatives. So this is the true negative rate, that's the specificity, that's true negatives minus nothing but true negatives divided by true negatives and false positives, meaning this is the false positive rate. If you invert 1 minus specificity, you get a false positives. Those are those that essentially were classified as positive by your logistic regression model, but essentially they were not admitted to whatever university of interest. So if you're depicting it in that way, you get here sensitivity as a function of your false positive rate. You get here that curve that essentially depicts for each of your entries, and these entries are consistent with the entries you've seen here in the histogram. For each of your entries, you basically get this curve and the area under this curve. So here, if you have 50%, if you look for the line of identity, you have here 50% of your entries. Everything above that 50% essentially gets your area under the curve greater than 50%, meaning this is better, your prediction is better than flipping a coin. And your total area under the curve, the perfect would be 1. So the greater it is, the better the diagnostic performance of your test. So if you, and this is important to keep in mind, if you're changing the threshold now, which we will do in the lab, you essentially get different sensitivity and specificities, and this needs to be kept in mind for the determination of the threshold, which is essentially where you use different approaches to determine that. So for the lab, we will use the admit safe data to fit a prediction model. And we will look into the interaction between GRE and GPAs, where you will create a predicted probability and you will create threshold vectors 0.075 by 0.01. You calculate 2 vectors, namely specificity and sensitivity, and you're plotting 1 minus the specificity, the false positive rate, versus sensitivity, which is the true positive rate. And this is the so-called ROC curve. Okay, but we will do that in a separate lecture. So this was today's lecture, and I'll be back in the lab in a second. All right, bye-bye.